Hello everybody, welcome to this talk. I am Anisur Rahman Molla. I am going to present our paper, Live Exploration with Mobile Robots in a Dynamic Ring Revisited. This is a joint work with Subhrangshu Mondal and William Kumar Moses Jr. So graph exploration problem is a very well known and well studied problem in the context of mobile robots. So it's basically you are given a graph and a group of mobile robots are initially distributed on some nodes arbitrarily. And the goal is to explore the graph. That means each node must be visited by at least one robot. In doing so, one important requirement is the termination condition. That means the robots must know that the exploration is completed and they could terminate. We studied this problem in dynamic ring. So dynamic ring is basically we consider the edge removal ring where at any time, at most one edge is missing. And this edge removal is controlled by an adversary. It's an anonymous ring, that is nodes are indistinguishable. And let's say multiple robots are placed in the ring on some nodes. And our goal is to explore the graph, right? And here live means live or online means like robots do not know what would be the next change, like what adversary will do next and at what time. And our goal is to satisfy these two conditions. One is exploration, another one is termination. So exploration means like each node of the dynamic ring must be visited by at least one robot. And in the end, the robot should terminate. Typically, like two types of termination is there. One is explicit termination, where all the robots know about the completion of the exploration and they terminate. Whereas the partial termination is like at least one robot know the completion of the exploration and terminate. So essentially, if there is exactly one robot, so explicit termination and partial termination is equivalent. This problem, like this exploration in a dynamic ring, was first studied by Diluna et al., which came in ICTCS 2016, and also came in this year Distributed Computing Journal. So they studied both in fully synchronous system and semi-synchronous system for two robots. So they shows that with two robots, explicit termination is possible with some mix of some assumption when, let's say, the robots know an upper bound of the size of the ring. So let's say, I mean, usually we denote the size by n. So if the size n is known to the robots, so it can be like explicit termination could be there. Also, they assume that there is a landmark. If there is a landmark node, let's say some distinguished node which is as a landmark is available, like it is basically marked as a like landmark node, then also it is possible to explicit termination, exploration with explicit termination. And also there is a notion of chirality, like a common sense of clockwise or anti-clockwise direction to all the robots. And if this chirality and landmark is given, then exploration is possible with explicit termination with faster than only knowing landmark. They also showed matching impossibility result when the size of the ring is unknown or no landmark is available. So let us just look at their impossibility result, because that actually motivates us to do this work, and also they left an open question there. So with two robots, they show that with the assumption, if there is no knowledge on the upper bound or any size of the n, and there is no landmark, then the partial termination is impossible, even if the robots are non-anonymous, like robots have IDs and chirality assumption. They also show that if we, on the top of that, if you make the robots anonymous, like robots do not have an ID, then any number of robots cannot solve this, this exploration problem, even if you have chirality assumption, like partial termination is impossible. So they left an open question there, like whether the exploration with more than 3 robots is possible when no knowledge of n is known, and also there is no landmark, but robot may have IDs. So in this paper, we settle this question in fully synchronous setting and also provide partial results in the semi-synchronous setting. So our results, let's see our results, like we actually present a fully synchronous deterministic algorithm. I mean, previous results are also deterministic. We also present deterministic algorithm for exploration with 3 robots, and we guarantee explicit termination when the ring size is unknown, there is no landmark, and there is no common chirality. But our assumption is robots, robots have unique IDs. And also we add another assumption, which is edge crossing detection. That means two robots moving in opposite direction through an edge in the same round, they can detect each other. Otherwise, what could happen that two robots, they jump from they're in the end point of a node, and they jump in the same round, so they cannot see each other. So there will be no meeting. If there is no meeting, so it's actually impossible to solve this exploration because our size of the ring is unknown. And also our running time, the running time is optimal, asymptotically optimal. It is n because n is the size of the ring. So another result, so now if you allow us to use random bits, then we don't need these two extra assumptions. The assumptions are robots have unique IDs and edge crossing detection. So these two assumptions, we can bypass that using a random bits. In fact, we present randomized algorithm for exploration with explicit termination using 3 anonymous robots, and where we do not assume edge crossing detection. This is actually in sharp contrast to the impossibility result of DeLuna et al., because they show that if robots do not have IDs, then any number of robots cannot solve this exploration in this dynamic ring. Well, I mean, then one may wonder whether this edge crossing detection or let's say randomness is sufficient for two robots to solve the exploration. It is actually not. So we saw this impossibility result also. Let's say with two robots, if the ring size is unknown and there is no landmark, then partial termination is impossible, even if robots have edge crossing detection assumption, chirality, and they have IDs, like non-anonymous robots. This means that edge crossing detection, it does not help you to solve exploration. On the top of that, if you give us, if you even assume that use the randomness, if you access to robots access to randomness, or let's say you use random bits, still it is explicit termination is impossible. That's what we saw. And finally, we actually extend our ideas to semi-synchronous system to achieve exploration, where we guarantee partial termination with 3 robots in the absence of landmark or the knowledge of n. And we follow the same semi-synchronous model considered by DeLuna et al. So let's go to the deterministic exploration protocol with 3 robots. And this is basically, in this talk, I just focus only this part. So let's quickly recap this network model and this assumption here. So we consider dynamic ring, right? So there are n nodes dynamic ring, which is anonymous, like nodes are indistinguishable, and we consider edge removal dynamics here. That means at most one edge is missing at any time, and which is determined by an adversary, and each node is connected via 2 ports because it's a ring. Right. And on the robots, what we assume that robots have unique IDs. And they're capable of edge crossing detection, like when they're crossing through an edge from 2 opposite directions at the same time, so they can detect each other. And we also assume that robot exchange information when 2 or more robots meet at a node or they crossing the edge. And we assume that robots requires for this, it possesses O of log n bits of memory. Now, as an adversary, so adversary knows the complete algorithm, also the states, because the algorithm is deterministic, also the states and position of the robots at any time. And with this knowledge, it has complete control on the edge removal. So it can choose which edge to remove. But it is allowed to remove at most 1 edge at a time. For the randomized algorithm, we assume that adversary is oblivious to the random choices made by the robots. So 50 points. This is like, we consider this is fully, this protocol now I am going to discuss is fully synchronous, and robots have no knowledge about the ring size, and robots do not have common chirality. So our goal is to explore this dynamic ring and achieve explicit termination. Our algorithm is divided into 4 stages. So first, what we want in the first stage, we want that any 2 robot meets anyway. We want first 2 robot meets. If the initial configuration is like robots are in the same node, that's fine. Then we can avoid like the stage 1. But just in the worst case, assume that the robots are in distinct nodes, like 3 robots. And we want the first meeting in stage 1. Then in stage 2, we want a second meeting. from the second meeting, what we want, we select one probe robot. So that robot will probe. I will tell you in detail in a few seconds. So then in stage 3, what we want actually the detection of exploration completion. So in stage 3, the exploration is completed and which must be detected by some robot. Otherwise, there will be no termination, and that's like important requirement of this exploration. And in stage 4, what we want to do, like in stage 3, essentially 2 robots detects that the exploration is completed, and in the 4th stage, the 3rd robot should be informed that the exploration is completed, so that everybody can terminate, so we can achieve explicit termination. Okay, so let's go to the stage 1. What is happening here? So we are assuming that robots have unique IDs, and we assume that the ID, let's say the ID length is the bit, the ID string length is k. So there are k bits in IDs. So now each robot, what they do, they actually can concatenate. Let's say there be k string, k bits, then again concatenate k bits, another concatenate k bits. So they can actually create an infinite bit. Let's say that's like their just like its own bits, IDs, and then IDs, so infinite bits. And what we do, so according to this bit value, let's say if the first bit is 1, then the robot moves to the right. Sorry, move to the left as we write. And if the bits is 0, it moves to the right. So by the way, this left and right, this is very local. Like I as a robot, I can choose, I can fix that, okay, this is my direction right and this is my direction left. So it does not matter what is left and right. So left could be clockwise or anti-clockwise, whatever. But one side is left, another side is left. This is completely determined by a single robot. So my left right might be different than the other robot's left right. So based on this bit value 1 or 0, I can choose go to left and right. And for each, like let's say for the ith bit, I move this, I fix this direction left or right, and I actually go to the power ith steps. That's the thing. And now this stage ends when 2 robots meet. What is the guarantee that 2 robots will meet? Because the IDs are distinct, so that these bit strings are distinct. So that means at least 2 robots, they have, I mean, all the robots, they have distinct bits. So at least 2 robots at some point, let's say ith position, their bit value would be different. And then that 2 robot go to the opposite direction. By the way, so that 2 different means does not mean that they go to the opposite direction, but they can move to the same direction also. Then what would happen, because this left right is different, then when they have different bits, they can go to the opposite direction. But anyway, this gives you, we can intuitively, at least 2 robots can make sure they are moving in opposite direction. So when they are moving in opposite direction, they must meet. I mean, there might be a block by the adversary, but there is a 3rd robot, they must meet at least one robot with another robot. And why this is? Because the adversary is actually removing only one edge. So by only removing one edge, it can block the movement of one robot. It can block movement of at most 2 robots when both the robots are in the end points of an edge and wants to jump to the opposite from the opposite direction. Then that removal of that edge would block the movement of the 2 robots at most, but it cannot block the movement of the 3 robots. So this stage 1 actually makes sure that 2 robots will meet. And when they meet, we actually, let's say, just for simplicity, mark them as A. One robot is A, which is the larger ID, and the smaller ID will get the ID B. And the 3rd robot, it did not be aware of this stage ending, because it is actually following this bit. Based on this bit, it's like this phase. Okay. Then just go to this quick example. So what is that? Let's say like there are 3 robots, R1, R2, R3. It is placed in these places like this R1, R2, R3, R2, R3, and they are moving this direction. Then what could happen? Let's say adversary delete this edge. Then what could happen? R3 cannot jump, but R1 can jump here and R2 can jump here. So then R2, R1 jump, but R3 is there. Then what could happen? Let's say adversary delete this edge, but this is not a good edge. I mean, then what could happen? R2 and R1 meets, right? Then when R2, R1 meets, then this stage 1 ends, and they put their name. R1 change to, let's say, A, and R2 change to, let's say, B. Okay. So now this is stage 2. Then what we do stage 2? So stage 1 is like we want at least 2 robot meets, that is done. So now what stage 2 we want? We want another meeting, the second meeting. Now, when AB, in the first stage, like A and B meets, then A and B start moving opposite direction, and they will never change the movement of their direction until the end. That's fixed. Now you see that when A and B are moving opposite direction, if they meet again, that means exploration is completed, and A and B know that exploration is completed. But the situation may not be that easy because adversary will block it. May not, I mean, can block it, right? So then what could happen? So A and B started moving opposite direction, and they also keep counting the number of steps they can successfully move. This respectively by variable step A and step B, because this way they can count the number of nodes actually in the ring. Okay, so now this stage ends when A or B meets the third robot, the R3, right? So when it meets the third robot, any of them, that's this stage ends. The third robot then, when it's meeting, it gets the mark C. Now either A and C or B and C know the stage 2 has ended, right? So this is like, let's say this is R3, the A and B started moving from to the opposite direction, and let's say adversary delete this edge, and R3 moves here. So in the next round, this is the situation. And now R3 is here, A is here. So A, B will never change the direction. So B cannot move because this edge deletion, and A can go. So now this is the, let's say adversary deletes this edge between R3 and A. So A and R3 cannot move, but B can move here. B is here. Now in the next thing, let's say adversary delete this edge, block B. Then R3 and C, they actually jumping towards the same edge. By the edge crossing detection assumption, we know that they can detect each other. And they basically, you can think of like they meet at a node. Why? Because when this happens, then let's say the one robot will wait in the another one node, and the other robot will, let's say A waits there because A has already, and C actually go back to A's place and meet. But simplicity, for simplest thing is assume that they can meet over the edge and they exchange information. And the R3 gets the ID, let's say C. Now the stage 2 finished here, and now we have stage 3. Now in stage 3, what would happen? Robots A and B keep moving on the same fixed direction. But what we'll do, let's say if A and B, so stage 3 is for the completion of the exploration, like detection of the exploration, how it will do. So if A and B successfully can go and meet, so that means exploration is completed. But it could happen that adversary blocks A and B, then what C will do, C will work as a probe robot. So C, the third robot, probe robot, it will start zigzag movement from A to B and B to A, and keeps a counter. What is the distance from A to B and B to A, right? Now, so this stage terminates when either A and B meet, or C finds A to B equals to B to A variable. So A to B means like the number of steps from A to B, and B to A is the number of steps from B to B, because C is maintaining this value, zigzag value, this counter. Now it is easy to say that if A and B meet on a node, then the step of A and step of B, because A and B also counting these steps, is N. If A and B meet on an edge, then A and N plus 1 would be the step of A plus step of B. Now if C finds A to B equals to B to A, then N minus 1 equals to A to B. So this is simply calculation, you can do that, it's easy to see. And then just look at this as an example in the stage 3. Let's say case 1. Let's say I have this robot A and B, and let's say adversary delete this edge, and C is moving this direction, because I said like A and B cannot change its direction, it is fixed after first meeting. So now what could happen if the adversary deletes this edge? So A and B can meet in this edge, right? So if this meets, then start stage ends. That means A and B actually detects exploration is completed, because A and B meets in the first stage, and then is the second meeting. Second meeting means, of course, like they are moving opposite direction. Second meeting means the exploration is completed. And this is one case. But what could happen that adversary can actually delete this edge, and it can block meeting A and B, right? So A and B cannot meet, but C is doing this movement from this side. So from A to this coming this side. Let's say the adversary actually keep this edge deleted until this stage finishes. What could happen? It's like block A and B, so that adversary, let's like I don't want to meet A and B. So it blocks permanently A and B. Whenever this edge is available, A and B can meet, because they can move. Then C actually doing this zigzag movement, because adversary only can remove only one edge, so it cannot actually block C. So C can go. Let's say C is going from A to B, so the distance from A to B like is 5, because it was counting this movement. And again, C will do this zigzag movement, right? So this way C will do. and it will say B2A is also 5. So when A2A is 5 equals to B2A 5, then C knows that A and B is blocked by an edge by the adversary. So, and the exploration is completed. Stage 3 ends. Then what we do, the stage 4. Stage 4 actually, because in stage 3, only 2 robots, any 2 robots, make sure that the exploration is completed. So they can terminate, but we want explicit termination. For that, these 2 robots need to inform the other robots that the exploration is completed. Then what we'll do, let's say A and C finds out the stage 3 end, the exploration is completed. Then what will A and C will do? A and C will move. A will keep moving its direction and C will move the opposite direction of A. And A also and C also knows the value of n, right? Now, because of this calculation, what is the n value? The number of nodes in the ring. So based on that, like C start moving towards the opposite direction of A for n rounds. So one of A and C meets B and terminates along with B. The other robot terminates after n rounds. Let's say C meets B, C and B terminates, and A actually keeps moving, and A can terminate after n rounds because it knows that in n rounds, C of course meet B. It does not meet B. Why? Because the adversary can block, because they are moving in opposite direction, the adversary can block only one robot, one of A or C, not both, right? So one of them must meet B. So this finishes, right? So this is an example. Let's say this A and C after meeting, A is moving towards its direction and C is moving this direction. And A, let's say they cross this edge. So that means A and B meet. So A, B actually can terminate and C actually can terminate after n rounds. So as a time compressor, it's easy to see that like stage 1 terminates after n plus n times 2 to the power k rounds, because we are actually doing this because each phase, the ith for the ith phase, the ith bit, if it is 1, it's actually moving 2 to the power I rounds. So n 2 to the power k basically. And typically k is constant, and all other stages like 2, 3, 4, because it's only moving to the opposite direction. So it actually takes n rounds. Like so 2, 3 stage, 4 stage takes n rounds. So total time is this n plus n to the power 2 to the power k, but typically n is constant. Sorry, k is constant. Why? Because for let's say 3 robots, like to have distinct IDs, like only let's say 3 bits is enough to have distinct IDs, right? In fact, like 2 bits is also enough. So typically k is constant. So total light time is n. So this is our like deterministic algorithm for exploring 3 robots. And if we go to the randomized exploration, like if we allow, like this is randomized exploration using 3 robots. If you allow us to use random bits, then we can remove this edge crossing detection and non-anonymous robots, like the unique IDs, this assumption. How? This is very easy. So how do you remove the edge crossing detection? So edge crossing detection means like when 2 robots at an edge, it wants to move to cross that edge, so they can detect. Now, what if I can make sure that one robot's wait and other robot jump to that node, then we don't need, right? So how do we make sure that? So for every movement, so when a robot wants to decide to move somewhere, so it tosses a coin, and if it is head and if the edge is present, it moves. If it is tail, it keeps there. That means with half probability, if two robots are on the end of an edge, with half probability they can meet, because with half probability one stays and one moves. That this one or this one, right? So that means in one full circle, like with 2 full circle in expectation, they meet. They might miss in one, but then that means essentially in n log n such cycle they must meet. Like with high probability they meet. And how do you remove this unique ID assumption? The ideally, like you can actually randomly pick, each robot randomly pick its own ID from some range. The range could be sufficiently large. So they knows that they have, like there are 3 robots, they can take, like to have unique IDs, they can take like from range 1 to let's say 2 to the power 3 square. So then with probability very close to 1, their IDs are different. All IDs, 3 IDs are different. So this way we can actually use, we can remove these 2 assumptions using random bits. And we know that because this edge crossing detection is taking L log n rounds. So essentially the exploration is completed, like the termination is with high probability, like 1 minus 1 by n, but the time would be on expectation L log n. Well, so as a summary, so this is our result. So I'm actually skip this semi-synchronous setting, semi-synchronous systems result, but for the fully synchronous with 3 robots, and what we show that with non-anonymous robots and edge crossing detection, we can solve this explicit exploration with O of n rounds. which is asymptotically optimal. Then if we use random bits, like we present randomized algorithm where we don't need these two assumptions, like the robots could be anonymous and there is no need to have edge crossing detection, then on expected n log n rounds, our protocol is terminating. And then in semi-synchronous setting, what we show that basically if there is no knowledge of n and no landmark and no chirality, then this protocol, we can extend this protocol to takes like fn rounds, where f is the largest time gap, time difference between the two consecutive activation of any robots, right? So because it's semi-synchronous, the robot may activate later, like it might be like it sleeps and activate, right? So this is the f is the largest time gap. And also this semi-synchronous setting, let me tell you, this is the probability guarantee. So we are actually using randomness here to, so it's like with probability 3/4 actually it terminates, like with constant probability. And we also saw that the impossibility result, impossibility result is, so with two robots, the assumption is there is no ring size is unknown and no landmark, then partial termination is impossible even if you have edge crossing detection assumption, and of course chirality and non-anonymous robots. And on the top of that, if you use random bits like edge crossing detection, and if there is edge crossing detection and random bits, still explicit termination is impossible. Um, so as a open question, so like as a very general question, one can try to extend this study to other dynamic graph classes like beyond a ring, and also different kind of adversarial strategies, like not only need not be like one edge removal, maybe multiple edge removing and some other different strategies. And of course, another thing is we are assuming in our algorithm that that the robots know there is three robots in the network. This number of robots is known. Whether we can remove this and design a exploration algorithm with explicit termination. Okay, so I'm done. Thank you for listening to this talk.